Hello everyone and welcome back. So today we're going to be talking about planar rigid body motion. And you should be happy to know we're getting closer to the end of the book. We're doing it. We're going to make it there. So what are we learning about? Well, we're going to understand the kinematics of a rigid body. Notice a rigid body here, not a point, but a rigid body. And it can rotate. Scary. So let's look at some applications here. First off, on this amusement park ride, all of these passengers are subjected to curvilinear translation because it's moving in a circular path. But they always remain upright, thankfully, because there's no seatbelts. Now, if you know the angular motion of these arms right here, could we determine the velocity and acceleration that all of these people experience? And why would we want to know those values? Well, probably to keep them from dying. Too much acceleration is a bad thing, everybody. Also, does each passenger feel the same acceleration? Person right here, is it the same as one right here? Like you always see, like the person in the back of the bus, they always say they get thrown up a lot higher when they hit a bump of the road. So is there something similar here? Well, we're going to find that out today. Also, with these gears, the pulleys and cams, they're all rotating about fixed axes and they're all connected together. And they can generate motion as well as transmit forces. But you have to understand that how these angular motions are coupled to properly design the system. So you have to figure out how to relate the angular motions of one to a separate. So this gear to this gear, or this gear to this gear. You have to figure out how they all connect. And you might be like, well, we did that. We did that already, didn't we? We did something similar to that at least. But no, not quite. There's going to be a difference to what we've done in the past when we start connecting these together. It's not quite so simple. So let's jump right into section 16.1, rigid body motion. So there are cases where an object can't be treated as a particle. That's when its size or shape actually matters. And when the size or shape matters, rotation matters. Like, for example, we're always talking about like the planes and everything else. And we were considering them as particles in many cases. However, in reality, when the wind is blowing on it and we have thrust, and drag and everything else pushing it, there's a whole lot of forces that are acting on this, and the shape matters. Otherwise, you have a plane that spirals to its doom. If you want like a terrifying video, look up flutter failure. Flutter failure. It sounds like butterflies. It is not. It is not. So, terrifying video for planes. So, continuing onward. If we're thinking about gears, cams, and links, we have to care about the rotation of that body. It's not staying stationary, it's spinning. And they're all connected together and they're sometimes spinning in different directions. So we're going to understand how to do rigid body motion today. But we're going to limit it to planar motion. Thank goodness no three-dimensional motion right here. Now, when I say planar motion, it's in the plane. So it's going to stay in the computer screen. It's not going to go out of your computer screen. So there are three types of planar rigid body motion. Rectilinear translation, right here, it just moves. But you see, it's not rotating. Curvilinear translation, it's going up and down, but you see that it's still not rotating. Just plain old rotation. And then finally, general plane motion, where it rotates and it translates at the same time. So, no rotation, just rotation, both. Okay? Those are the three types we're going to be looking at. So, obviously the translation is fairly similar. It's more or less what we've done in the past, because there's no rotation. And so every single point in that rigid body, they're all moving in the same exact path, just in parallel paths. Now, if those paths are curved, then it's curvilinear. So straight paths, rectilinear, curved paths, curvilinear, which makes sense. It's curved, it's curvilinear. What about rotation on a fixed axis? Well, in this case, all the particles are moving in very similar circular paths. And all these particles are in planes that are perpendicular to the axis that they're rotating about. Okay, so it is moving, and this little circular plane right here is perpendicular to that axis. And finally, general plane motion, it's just going crazy. They're having translation and rotation all at once. And this looks really difficult, and it is more difficult than our previous two cases, but it's not terrible. We will develop methods for working with it, and after a couple examples, I feel like you're going to just rock it. Okay, so let's look at an example of planar rigid body motion right here. So we have three different types of motion happening in this system. We have rectilinear motion right here, so rectilinear translation, because it can only move in a straight line back and forth. This one has general plane motion. It's moving back and forth and it's rotating at the same time. This one right here is undergoing curvilinear translation. It's going to stay flat the entire time, but it's moving through a curved path. And then finally, these two are rotating about a fixed axis. So we're seeing everything here. And I always jump ahead of myself, so, and there we go. So, what I've just said, written down again. Sorry, I will jump ahead in my PowerPoints. You know what happens. Okay, so the last thing we're going to talk about this time is rigid body motion translation. We'll jump into the other types next time. So, first off, for this rigid body motion that's moving through translation, we have to first find a position coordinate between our origin of our fixed coordinate system and this body that's moving. Now, what we also realize is that there is a translating coordinate system too. I have my origin right here, but I pick a point, in this case point A, and I say, okay, you're now my origin inside of my body. Because remember, in just regular translation, not general plane motion, there's no rotation here. So this relative position vector between A and B is constant. Okay, it's constant. So when I look at this equation right here, what I see is that, well, this is going to be 0 because they're not moving with respect to each other. And so the velocity of B and the velocity of A are going to be the same thing. And also the acceleration of B and the acceleration of A will be the same thing, because they're moving along parallel paths at the same rate. So for a rigid body to be only in translation, whether curvilinear or rectilinear, all the points have to have the same velocity and the same acceleration. Okay, that's it for this time. Thank you so very much for listening, and I'll see you all later. Have a wonderful day. Bye-bye.